Welcome to Krohne's e-learning module Coriolis Mass Flow Meters. This module is the first of two parts and will give you some basic knowledge of Coriolis flow meters. As an introduction to this module, we would like to tell you about the learning targets. When you have finished this module, you will have an overview of the history of the Coriolis principle and how it affects our daily lives. You will be able to describe the measuring principles and measuring techniques of the Coriolis mass flow meter. And you will also have become acquainted with the relevant physics important in understanding the measurement principle. You will be made aware of the process of calibrating Coriolis mass flow meters. Also, the various construction types of Coriolis meter will be described and the advantages explained to you. You will then be shown the process of sizing and the sizing tools for selecting Coriolis meters. And finally, in this module, we will show the importance of material selection for Coriolis mass flow meters. So, let's get started. So, starting from the beginning, what is the Coriolis effect? The Coriolis effect was first discovered by Gaspard Gustave de Coriolis, a French mathematician specializing in mechanics and kinetic energy, who became interested in the transfer of energy in a rotating system. He defined the Coriolis effect as the apparent deflection of a moving object in a rotating frame of reference. This is sometimes called the Coriolis force. The principle is explained more practically by a plane flying internationally. Let's consider a plane flies from South Africa to Poland. While the plane is in the air, the Earth rotates below. If the pilot did not correct for the rotation of the Earth and flew directly in a straight line north, and you are able to watch this flight from the North Pole, the plane will look like it's moving in a curved path. Therefore, the pilot has to correct for the Earth's rotation during the flight to reach the destination successfully. To demonstrate the Coriolis principle again, we can look at a child's playground carousel. When the carousel is not rotating and a ball is rolled from the center to the edge, the ball will roll in a straight line, and it will appear to those children on the carousel and those watching from around the carousel that the ball rolls in a straight line. Now, if we repeat this with the carousel rotating, the children on the carousel see the ball curve in its path as it moves from the center to the edge. But those children watching from around the carousel still see the ball going in a straight line. A mass flowing in a measuring tube now replaces the ball on the carousel. The tube can rotate clockwise, or the tube can rotate anti-clockwise. If we reduce these rotations from full rotations to small angular changes, we can oscillate the tube through very small angles of rotation. These small oscillations are the principle used by the Coriolis mass flow meter. Now looking at the mechanical system of the mass flow meter, the system is oscillated by the central driver. The fluid flows through the tube and tries, like the plane or the ball, to travel in a straight line. The fluid mass has momentum, and even when contained in a tube, continues to try and travel in a straight line. The inertia of the fluid distorts the tube with a force, Fc. But the tube only allows the tube to deflect until the tube exerts an equal and opposite force on the fluid, Fr. This reaction force is implied by Newton's third law. To each action there is an equal and opposite reaction. Therefore, Fc equals minus Fr. The small deflection of the tube is accurately measured by the Coriolis mass flow meter. Let us now see how these forces are measured. In a twin-tube Coriolis meter, the driver resonates both tubes, and the sensors A and B measure deflections between the two tubes. In operation, the driver oscillates the tubes with a very small amplitude of around 0.1 millimeters. The amplitude is exaggerated in the diagrams to demonstrate the principle. The oscillation provides the angular velocity, W, required by the Coriolis principle. The driver oscillates the tubes at the resonant frequency of the system. It will be shown later that this resonant frequency can be used to measure the process fluid density. When there is no flow and the meter driver is not working, there is no driver oscillation. Therefore, the sensors A and B measure no deflections. When there is no flow, the flow velocity V is equal to 0, and the mass of a unit of fluid in the tube has no inertia. Therefore, the mass exerts no forces on the tube walls. When there is no flow and the driver is running, the two sensors measure the same tube deflections at each end of the tube at the same time. However, when the flow is greater than 0, the inertia of the fluid mass tends to flatten the curve of the tube on the incoming side and push the tube outwards at the outgoing end. With flow greater than 0, the Coriolis meter continuously measures the deflection at both sensors A and B, and calculates the time shift of the sinusoidal oscillation between the incoming and the outgoing sensor caused by the Coriolis effect. We can draw the amplitude of the sensor measurement with time for both sensor A, shown in blue, and sensor B, shown in orange. When the flow starts, there is a time shift between the measurements at sensors A and B. This effect is caused by the deflection of the tube explained previously. The resulting time shift is proportional to the mass flow rate. Therefore, as the mass flow rate increases, so the time shift increases. The Coriolis mass flow meter, due to the symmetrical design, performs equally well with reverse flow, and is therefore a truly bidirectional instrument. We can now look at a simulation showing the true distortion of a twin straight tube Coriolis mass flow meter under operating conditions. Please note the distortion is exaggerated so the effect can be visualized. Let us now relate the theory of Hooke's law to a Coriolis mass flow meter. The mass of the spring system M equals the mass of the tube, M tube, which is fixed, plus the mass of the fluid in the tube, M fluid, which is variable with the process. The mass of the fluid in the tube is calculated from the volume of the tube, V tube, which is fixed, multiplied by the density of the fluid, ρ fluid, which is variable. For a known meter, the mass and the volume of the tube are fixed, and as a result are constant. Therefore, rearranging and substituting the equation, density ρ fluid equals the spring constant K divided by the frequency F squared, multiplied by the fixed tube volume V tube, and the constant 4 pi squared, less the fixed values of the tube mass divided by the tube volume. However, with all the variables fixed except for the frequency f and the density ρ fluid, the frequency is inversely proportional to the square root of the density ρ fluid. The Coriolis mass flow meter continuously drives the sensor at the resonant frequency f, and by measuring this frequency, we calculate the density of the process fluid ρ fluid. Having seen that the Coriolis mass flow meter can measure both mass and density, the Coriolis mass flow meter can also be used to provide a calculation of volume flow rate and total volume. This is due to the fact that the volume flow rate equals mass flow rate divided by the density of the product. The Coriolis mass flow meter has a third direct measurement capability, that of temperature. The process temperature changes the Young's modulus of the materials, which affects the stiffness of the measuring tube with temperature. Also, temperature causes thermal expansion and contraction effects, which affect the stresses on the measuring tube. To correct for these effects, the Coriolis mass flow meter measures the temperature of the measuring tube with a platinum resistance temperature detector, RTDs. The Coriolis meter uses thin wall tubes for the mass flow measurement, enclosed in an outer case. The RTD is bonded to the outside of the measuring tube with a thermally conductive gel to ensure good heat transfer to the sensor. This gives a good indication of the process fluid temperature. Therefore, the temperature data is also made available to the user and the control system. Having density measurement and temperature measurement capability allows the Coriolis mass flow meter to be used for concentration measurement of Plato, bricks, Baume, and alcohol. The calibration of a Coriolis mass flow meter is complex and involves characterization. To evaluate the behavior of mass or volume flow and density measurement with temperature, and similarly to evaluate the behavior of mass or volume flow and density measurement with strain gauge values. Only once the characterization is complete do we conduct the calibration for mass and volume flow rate using highly accurate weigh scales. From the evaluation, unique characterization and calibration coefficients are calculated for each individual meter. Finally, verification testing of the calibration and characterization is performed, and only on successful completion of the testing are the calibration certificates printed. The calibration must be accredited to give confidence to the performance of the meter. Therefore, all calibration rigs must be certified and traceable to national and international weights and measures standards. These certifications confirm the typical calibration rig uncertainty to be about 0.03%. The calibration process uses characterization at 3 temperatures for straight tube meters. Mass and volume flow rates are calibrated using water only. Independent testing proves the correlation to all fluids, liquids and gases with differing densities and viscosities. The density is calibrated with air and water. The calibration rig certification includes, for mass flow, volume flow and density measurement according to ISO 17025. EN ISO standard to demonstrate competence to carry out tests and or calibrations. Independent of the physical construction of the Coriolis instrument, all use the same fundamental principles. Historically, Coriolis meters have been of a twin bent tube design to improve signal strength when electronics could not accurately discern the very small time shifts induced by the fluid mass flow rate. Many designs have been used from the classical U and V tube designs to omega profiles, along with S and Z profiles and coiled construction. All of these designs commonly have the driver and sensors mounted between the tubes to amplify the physical deflections. Single bent tube meters have used many of the same profiles, but the U, S and Z profiles are the most common. In this case, the driver and sensor measurements are referenced from a rigid support structure. Twin straight tube meters provide a similar amplification capability to a twin bent tube design, but offer advantages of lower pressure drop and secondary containment inherent in the design. A single straight tube meter provides the lowest pressure drop, with the measurement again being made to a rigid reference structure. The meter structure is similar to the twin straight tube meters and offers secondary containment and ease of installation. So, when specifying a mass flow meter, what design do you select? Historically, twin tube meters have had performance advantages over the straight and single tube designs. But today, with modern sensor and electronics design, this has practically been eliminated. You are now able to focus on what is best for your process. Consider the process advantages of a single straight tube. For maintainability, the straight tube is self-draining, easy to inspect, cleanable, and piggable. It is possible to pass a pipeline inspection gauging unit through the meter. The straight tube design provides the lowest pressure drop whilst providing a high accuracy. This makes a single straight tube meter ideal for applications involving slurries and abrasive fluids, shear sensitive fluids, and high viscosity fluids. The structural design of a single straight tube meter offers the added safety advantage of secondary containment. The sensor sizes for single straight tube meters are typically from DN06 to DN50, but DN100 instruments are available. Then let us consider a dual or twin straight tube meter. The higher turn-down ratios improve measurement at low flow conditions, with capability for high accuracy. This, along with the reduced flow velocity in the meter, makes these meters ideal for low-density fluids such as gas applications. The maintainability advantages of twin straight tube designs are self-draining, easy to inspect, and cleanable. Generally, twin straight tube meter designs can operate at moderate temperatures up to 130 or 150 degrees Celsius depending on manufacturer. The twin straight tube designs are available from DN15 up to DN300. Dual or twin bent tube meters are used for both general purpose and high performance applications. They can provide wide operating ranges, offering options for high accuracy and turn-down ratios of 1000 to 1. Maintenance and installation options are reduced for bent tube meters, but some designs are self-draining if installed to the manufacturer's instructions. Twin bent tube meters can have wide temperature ranges, with cryogenic versions or high temperature versions up to 400 degrees Celsius. The increased signal of some designs can allow thicker tube materials to be used, which can offer higher operating pressures. The line sizes for twin bent tube meters are from DN2 up to DN400 depending on the manufacturer. Having looked at the principal tube designs of the Coriolis meter, we will now briefly review sizing. The Coriolis meter requires specialist sizing tools, as the nominal line size is rarely suitable. For liquids, the process data of temperature, pressure, density, viscosity, and flow rate is all that is required for the sizing to be calculated. For gas applications, the additional data of the molecular weight, ratio of specific heats, and compressibility factor are required. Coriolis meters are not affected by flow profile. Therefore, the Reynolds number does not need to be considered or calculated. The sizing tool takes into account measurement error, pressure drop, and flow velocity. We will now demonstrate a typical sizing for a liquid application. The sizing example that follows uses the krohne Kroh-Maskal sizing program, which is available free of charge. On opening the program, you can select the product family you wish to conduct sizing on. OptiMass for the general product portfolio, OptiBatch for the OEM specialist filling and batching meter, and OptiGas for liquid sizing applications for the specialist high-pressure gas meter. For this exercise, select OptiMass for general application sizing. Having selected OptiMass, we are now at the data entry screen. Firstly, you can enter project-specific and tag information into the data table. Secondly, we can enter the process information. For this example, we have selected the state liquid from the pull-down. We can now enter the process data. This can be done in one of two ways. Either select the process fluid by entering the data manually, or by using the question mark. We will select the question mark option, which opens a selection box. From this, we now select the operating fluid, hydraulic oil. We now manually enter the temperature, 30 degrees Celsius, and the pressure, 35 bar gauge. We can then select Calculate, and the density and viscosity will be automatically calculated. We then check the data and select Accept Values. Finally, for the data entry, we enter a maximum flow rate. For this example, select Flow Type, Mass Flow, and enter the maximum flow rate of 1000 kilograms per hour. The data entry is now complete, and we select Calculate Meters. Having selected Calculate Meters, we have now entered the sizing page. For this example, enter the tube material as stainless steel only. Note, always verify the material compatibility of the wetted parts and the process fluid. The sizing program provides a list of possible suitable meters. The four in this example highlighted in green are preferred options for liquids only. You can now select an individual meter and review the pressure drop, flow velocity, and error curve. Always consider the actual range of operating conditions in your decision making. For example, the OptiMass 1000 S15 is already working in its lower working range in this application. Select the OptiMass 8000 S15 for a high turndown capability, but for minimum pressure drop, select the OptiMass 7000 S10. These files can be saved as editable Kroh-Maskal files, as PDF sizing sheets, or emailed directly from the program. Sizing is not the only consideration. We must also give care to the selection of the wetted part materials. Avoid tube failures. Select the correct wetted part materials to suit the process fluid. This is an example of a failure where a titanium measuring tube was used on a methanol application. Industry standard corrosion guidelines are not suitable. This is because these guides are written for process pipework thicknesses, not those used on Coriolis meters, and are therefore not suitable. Mass flow meters, as already discussed, use very thin-walled tubes in their construction. Therefore, A low corrosion rate in a standard table may have a significant percentage rate of wall thickness reduction on a Coriolis measuring tube. So, to be sure, take guidance from the instrument manufacturer and use the Coriolis meter manufacturer's corrosion tables. Having completed this first module of Coriolis mass flow meters, you will now have an overview of the history of the Coriolis principle and how it affects our daily lives. You understand the measuring principles and measuring techniques of the Coriolis mass flow meter, and you will also have become acquainted with the relevant physics which helped you to understand the measurement principles. You will now be aware of the process of calibrating Coriolis mass flow meters. Also, the various construction types of Coriolis meter will be familiar to you, along with their advantages. You will have seen the process of sizing and the sizing tools for selecting Coriolis meters. And finally, you became aware of the importance of material selection for Coriolis mass flow meters.